entropy has been a favorite topic of mine for years. I mean, I have a number of times I have solved research problems using entropy, and equally maybe more times in which I thought I had a proof using entropy in it, and it all crashed and burned because it's a complicated thing. And maybe 6 months ago, again, I was reading up on why entropy always increases, and they were sort of saying it's more subtle than you'd first imagine, but it's still worth everybody knowing a little bit about entropy. So I guess this guy back in 1800 defined entropy for thermodynamics, and it's a measure of how much order there is. And you can see this is a very highly ordered thing. And if you blow it up, then it's very unordered, right? All right, so the official definition is if I tell you what, so the macro, view of the world is I see this is the table and this is the chair, right? That's the macro world. And the micro world is where I know where every particle is, how fast it's moving, right? It's direction. Right. So the idea is if I tell you the macro world, I tell you it's a gas, I tell you it's a table, then how many different states could it be in? It's just a counting thing in the micro world, right? So a gas, I tell you that it's this box with such pressure and such temperature, then I kind of know the average speed, but there's still every particle is moving in a random direction, right? But if I tell you about this table, well, more or less everybody's where it's supposed to be, right? And then he took the log of that number. Now you might ask, why do you take the log of it? And my bet is the reason he did it is that if you have one object and you want to know the number of possibilities, and you have another object, so the entropy is the log of that, right? So now if you have two similar objects, the number of possibilities is n squared, right? Because you have so many possibilities here times so many possibilities here. Where if you take the log of it, it becomes the entropy doubles, right? And that just feels better that if we double the size of our object, then the entropy doubles, right? I think that's the story. Right?
Oh, hi, can you hear me?
I can hear you.
Oh, okay, great. So I'm wondering, for the equation here, for example, the entropy equals to log n, we only need to memorize it, right?
I am never going to test you on it.
Okay, great.
So I think you would be a more rounded person if you understood entropy.
Okay.
All right. This is physics. We're doing a page of physics here, and it won't be on the test. All right. All right. So right. So yeah, we have to tell you the velocity of each particle, right? And so now Shannon, much later, we'll see his picture in a minute, related it to information. And the reason it's important to us in computer science is because in German they call it Informatik, right? It's all about information. And so another way of thinking about the log is if I wanted to tell you, given the macro, I wanted to tell you what the micro state is, then the number of bits I would need to communicate is the log of the number of objects. Okay? Everybody got that? If you have n objects, it takes you log n bits to describe an object, right? And so you can describe it with a binary string. And you need fewer bits here, and you need lots of bits here. All right, so Shannon, I promised you Shannon would come in. And look, just right after the war there, right when a lot of great things happening. You know, Turing was doing his Turing machines, and Gödel was doing his incompleteness theorem. Anyway, we're going to now talk about communication complexity, and going to make this a little smaller and out of the way a little bit. All right. Right. So the baby has a bunch of toys and needs to communicate to Shannon which toy he wants. Right. And he wants to communicate it using bits. And we want to communicate with as few bits as possible. Right. So there is, you know, he's communicating with bits. And of course, Shannon says, great, but I don't know what that means. We need a code, right? So here we could give a code to our various objects, right? And when the baby communicates this, which toy does he mean? Well, you think he probably means the car, the red car, right? But why do you think I have this example here? Is he might mean, I want the potato man and I want the robot, right? I'm going to see that because it's, and so, so what we're going to do is we're going to require that no code is a prefix of another code, right? And the way we're going to do it, one way of achieving that is with what's called a Hoffman code, after, I'm sure, Mr. Hoffman. And so it's a binary tree that's sitting on the leaves or the objects, right? And this is the same sort of binary tree that you would get if you were playing 20 questions, right? So the baby gives a sequence of bits, and you go 0, 0, 1, 0, 0, and you get a duck, right? Everybody good with that? And if the baby says something longer, then you first following get a duck, which gets so many bits, right? And then you go 0, 1, 0, and get a lion, right? And then you go 1 and you get a dog, right? Everybody good with communication? All right, so now you might ask, why do some objects have shorter codes? And it's because they're more likely, right? If all our objects were equally likely, we would give them all the same code length. But, you know, we expect that the baby likes this dog. So we give the dog a shorter code, right? Yeah. I would say that it's not as much of it. If you want to have it so you can string together codes of different lengths, then it all boils down to not having a prefix, and it all boils down to a code like this. Right. 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 Yeah, it boils down to giving some sort of code, and right. Yeah. Yeah. Well, you haven't even think how you're going to store it, how you implement it. In fact, I had a co-op term at Waterloo when I applied to all these places in Germany, and I had to, in machine code, write something that would do sort of like this to compress images. All right, so here, what are we doing? Well, PI, for every object I, we'll have PI be the probability that the baby chooses the ith toy, right? And we'll have LI be the length of its code, right, for object I. And so here you see I put probabilities on the bottom, and as you can imagine, those add up to 1, right? And the Li is the depth of the path to get to the object, right? And what we're trying to minimize is the expected code length, right? So the game is you flip coins to choose a prize according to this distribution, and then your cost then is the number of bits you send, and we want the expected cost. And if you're all up on expectations, people know enough probability to know expectations, right? It's kind of a weighted sum, right? If all of these were equally likely, then all of these would be 1 over n, right? So it would be the sum of the lengths divided by n, which would give you an average, right? But this is weighted by how likely it is, right? All right, so we are, of course, doing, this is the greedy section here. And so we need a problem that we need to compute. And the problem is the input tells you the probabilities of your objects. And what your algorithm needs to do is to find a binary tree like this. So it determines, it has to choose how long to make each message, right? And then the expected length of the message will be called the entropy of the distribution, right? Does that make sense? So if you want to just as a quick check, tie it back to our thermodynamics, right? If there was capital N different states for your system to be in, then for me to tell you one of those states, I'd make every L log n, and I guess certainly the original thermodynamics guy wasn't giving different probabilities to different states, but you could do that. But it all boils down to the entropy would be log n, right? Does that make sense? Yeah. No, 0, 0, 0, 0, 0, 0 is the code for the red car. Yeah, if you do 0, I would be waiting for the next bit. Exactly. Are people following what we're doing here? All right, so let's do communication entropy, right? As I said, our problem, the input are the probabilities of your objects. The solution is a Huffman code. The cost of a solution is the entropy, it's the expected length of the code. Right, and the goal is to, of course, minimize the expected number of bits, right? So we need a greedy algorithm, and right, we put all our objects, and it would be kind of adaptive greedy, and it's going to be a little odd greedy. I bet you anything, if we look at my father's very concrete definition of matroids, this just will not, might be too weird, but maybe you can get it in there. But anyway, we're going to have a priority. All the objects have a weight, and we're going to sort them in a priority queue by their probability, right? And so now, as a greedy algorithm, we're going to have to say, well, which object do we want to make a decision about first? Now, there's a problem with that. First off, well, you would think it is either the highest, the highest probability or the lowest probability. But even what does it even mean to make a decision about it, right? It's not like we're taking them, not taking them, right? We're building a tree, right? So let me tell you the objects that we're going to consider first, and you try to think about what we will do with them. All right, so I'm going to grab the lowest 2 probability objects. What do I want to do with them? Remember, we're building a tree, yeah? Yeah, exactly. We're gonna add the probabilities. And when we add the probabilities, how are we gonna handle these two objects? We're gonna put a little tree on them. Exactly. You take the two objects with the lowest probabilities, they should have the longest codes, right? So we're gonna make their codes a little longer. And the way we're gonna make them longer is we put them in a little tree, right? And in some ways we reduce the whole problem because we can think of those two objects now as one object whose probability is the sum. And if you want to communicate one of them, you first communicate that you have one of them, and then you have an extra bit to tell you which one, right? Does that make sense? All right, so that was great. We joined them into one object, we sum their probabilities, and there we have it. And then you repeat, right? So when we repeat, we sort our objects based on their probabilities, right? And you'll see this guy bubbled up to some place, right? So then we do it again, right? We take the two lowest, we put a little tree on them, we add them up, we bubble it up. Everybody following this? Same deal, little tree, bubble it up. Now you'll note we're grabbing two objects, but that's a joint object. So we both put a little tree on it, right? And we bubble it up. And then these guys, 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 right? Everybody buy that? That's the algorithm, right? You can see it's a reasonably natural, greedy kind of algorithm that you might want to try, right? And the question then is, does it give you the optimal solution or not, right? Let's see. Yeah, and then of course it ends with a 1 at the top, right? Because it's kind of one object. All right, and that was that. All right, so now we're going to go through our steps again, right? If you want to be talking about loop invariance, right? We've gone somewhat through the algorithm. The algorithm has done some things. AT minus AT is the object that it's decided upon, and we're claiming that there exists an optimal solution consistent with that, right? Everybody good? So we can talk about how to establish that loop invariant, because at the beginning no decisions have been made, and then how do we maintain it, right? If loop invariant at time t minus 1 is true, then we know that there's this solution that the fairy godmother is holding for us, right? And then the algorithm commits to the next object, and we then have to massage what she has into ST and prove that it's still valid, it's still consistent with what the algorithm has done, and still optimal, right? Everybody buy these things? And so it comes down to playing the game, right? So here's this is the game in question that we're going to be focused on, right? And I actually have made up most of the test 4 as well. I'll have a few chatty questions about the context in general, and then we'll play this game. All right, so far, right, the algorithm has taken a bunch of objects and merged them into this tree, and to other objects emerged into that tree, right? Everybody kind of get the picture, right? And these are the weights of the resulting tree, and she's holding a full solution consistent with that, So she has a full binary tree. And because it's consistent with you can see how the purple triangles are hanging off as kind of leaves, as subtrees of her bigger solution. All right, everybody see that this is that the purple triangles is what the algorithm has done so far, and she's giving a full solution consistent with that. Everybody buy that? All right. So then the algorithm comes, and he takes the objects that have smallest weight and he merges them together, right? So that's those guys, right? And so merging them is going to be inconsistent with what the fairy godmother has done, right? Because she doesn't have them in a thing. So what we're going to do, how are we going to rearrange the tree, you think? And remember, let me restate, because it used to frighten students and we changed the rule. There's no promise that what she's giving us is optimal, right? She's just giving us something. All right. So we want to change her solution so that it's at least as good and it merges those two together, right? So these two definitely have to get merged together. And what length should their codes be, right? Well, we don't know their their code up to here should be longer than the code for this guy, because it has right? You can see it's not completely optimal here. This guy has a much smaller weight than this one, if you think about it as an entire object, yet it has a longer code, right? So that's saying that they're not optimal, right? So if we we can't mess up the triangles, and our life will get confusing if we mess up her tree. So instead, let's just rearrange things. Where should we put these two triangles? We're gonna just put them down here at the bottom, right? So this was a 0.2 and a 0.1. And so where are we going to put them? We're going to put the 0.2 and the 0.1 where those ones were, and we move those down, right? Does that make sense? And so that was our instruction in how to change her solution, right? Everybody kind of get what we're doing, how we're doing it? Now we want to see, is it consistent with what the algorithm is doing, right? We didn't mess up the previous decisions were the triangles. We didn't mess up that. And the new decision was that these two got put together. We didn't kind of say we don't know where they are in the world, but we know they're together, right? So at least we got them together. And so it's definitely consistent with what the algorithm has done, right? Is it valid?
No.
Oh, no. We got a voice from the world. Why is it not valid?
So if we pay attention to the weight of the edge of each bit, then we'll find that the 0.2 has 0, 0, 1, and 0.1 one has
So yeah. Are you asking? Let's separate that into two questions. One, is it valid? Is it a valid solution? And the other question, is it an optimal solution? So does anybody have an idea what valid solution means? It's a binary tree, right? The answer is that it's a binary tree with the objects at the leaves, right? So is it a binary tree?
Yes.
Yeah. All right. So now we can ask, is it optimal? And we kind of observed it wasn't optimal before, so it's probably not optimal now. What do we need to prove? Yeah, we just got to show that it's better than what the fairy godmother had, right? Does that make, are you good with that?
Yes.
Right? And so, right, so here, a bunch of text, so it's, right, we said all this, right? This is just some tree, yeah. Yeah, it's valid because it's a binary tree. With the, yeah. Well, is it a binary tree? Then it's a valid solution, right? No, no. In fact, it's not optimal. But what we have to prove is it's at least as good as what the fairy godmother had, right? And so now optimal. Well, we're saying it was optimal, but that's all the lie, right? Because it's not optimal, and that's what was messing people up, right? But we have to show that this sum goes down. And the reason it goes down is because, right, this was the 0.2 used to have a length of this, and we moved it up, right? So that made it better. And the point, right, the small ones moved down and the big ones moved up. And so if you try to, you could argue that that makes this expected value better, right? Everybody buy that? And that's the entire proof, right? Right, and then we get to the end. Everybody good with that? All right, so now just because I'm kind of obsessed with entropy, and we are doing computer science after all, let's just fit it back into, bring Shannon back into it. Yeah? No, no. No, so let's review. This is a very good question, all right? So what we did, our game, let's focus on the game. The game is the algorithm gives us AT minus 1 and later gives us AT. The fairy godmother gives us ST minus 1. That is definitely valid, definitely consistent with AT minus 1, right? And may or may not be optimal, right? But it may be optimal, right? And what we're producing is we're producing ST. And we need ST to be consistent with what the algorithm has done and valid. And now we're just saying it needs to be at least as good as what the fairy godmother had, right? And the reason we do that, the reason we allow the fairy godmother to give us something suboptimal is because we do have to consider all cases, right? And I don't really understand optimality as a poor little guy standing up here, right? So I don't want to be worrying about is what she gives me optimal or not optimal, right? I'm going to just focus on is it better, right? We just don't want to, and that assures us that we handle all the cases, right? We're handling, this is a case that she could give us this, and maybe it was optimal. But then we would have to say, well, it is a case, but it's not optimal, right? But that just doesn't seem like the smoothest way to go, right? The smoothest way to go is saying, I don't care if it's optimal, I will make it better, right? Or at least as good, right? So we proved the game, right? Because we proved that doing this switch made our solution better than her solution, right? So yeah, so now that we know that the greedy algorithm returns the optimal solution, do we know that? We do know that. We do know that. And I gave kind of two proofs for it, right? The one proof is using loop invariance, right? Do we maintain the loop invariance? And as you can see here, it says if ST minus 1 was optimal, if the loop invariant was true and she did give us an optimal thing, then we're getting something that's at least as good. So it's still optimal, right? So as long as you start off at the beginning, the algorithm hasn't made any decisions. So really the fairy godmother could hold anything, right? And she might as well hold an optimal solution. right? And then we keep changing what she has. So what she keeps has changes, but it remains optimal until the end. It's optimal what the algorithm has, right? Yeah.
The best solution for that case, then we just run it, and we can't really change anything, right? Or would we say that? Would we just repeat what the fairy godmother said and say it's optimal because it is?
So the way I'm recommending us do it now, I think it's easier, is when you're playing the game, all you know is she's giving you a solution that's consistent with the algorithm and it's valid. We don't know whether it's optimal, and you just have to make it at least as good, right? That's the game. And then on the outside of that, you should know that if you do that, then the greedy algorithm works. Why? Because one possibility is that she's holding an optimal solution, right? And if she and then we're maintaining that she's holding an optimal solution, right? So that's one proof. And you might remember I had this other proof which said the potential value of AT minus 1, right, is the maximum if we're trying to maximum, or minimum if we're trying to minimum, of over all S consistent with AT minus 1 of the value of the solution, right? So it's also in the slides.
Thank you.
But it basically says, look at you where you are right now in your life. Right? Your past is not going to change. Right? What is the absolute best you can become? Right? That's your potential, right? It's the absolute best that you could come, conditioned on what we have now. Right? And so when you go from the potential value of this to the potential value of this, right? Then, well, we know, can the potential value get better? It can't get better because this maximization is over a larger set of things. More things are consistent with this than with this. When you go from here to here, all you're doing is burning bridges, right? So this can't get better. But if it doesn't get worse, then this last step was somehow a reasonable thing to do, right? It's what I was calling globally optimal, right? If these are equal, right, then we have this whole sequence with potential value of A0, right, equals, right? Remember we had that whole sequence. And the potential value at A0, well, everything's consistent with A0, right? So that this equals the max, this is the optimal solution, right? And down here, when we're all the way down to our our end, right? Then our potential is just the value this. That's the only thing consistent with it, right? And so that told us our value here, our value at the end does in fact equal the maximum. Right? Does that make sense? So those are two different proofs that really are the same proof, right? Right? And what I'm doing is maintaining the loop invariant I'm maintaining is that my current potential value, I'm saying there exists an optimal solution consistent that's consistent, right? So that's telling me that I'm still equaling the optimal value. But my loop invariant is that my potential is always optimal, right? And my potential never goes suboptimal, right? That's the loop invariant. Yeah?
And so for, when
when we are proving it, we need to discuss like cases, like if one of the lowest possible items are on the correct position and the other one on somewhere else, then we just move one. If two of them are not there, so we move two. Do we need to discuss like cases?
There are cases. The cases are based on what are the possible ATs and the next thing that the algorithm does, right? Here, usually we have a case here. I commit to the next object, I don't commit to the next object, right? And we also have cases based on what does the fairy godmother hold, right? Maybe she holds another quarter, maybe she holds 3 dimes, maybe she holds, right? So those are lots of cases, right? In fact, you can kind of think about I always like a tree of cases, right? We have AT accepts the next object versus it rejects. And then we can branch on ST minus 1 has 1/4, has 1/4, or it has 0 quarters. Right? And then we could branch on, well, if that's 0 quarters, how many dimes does it have? Right? I kind of put that in that's in the slides now, right? So you can see it's the tree of possible cases. And what I removed from this is worrying about whether this was optimal or not, because that was just messing up our cases discussion. It just wasn't helping, right? Because here, in fact, in some ways, this was a really easy proof because we didn't have any cases, right? The algorithm always is going to grab the 2 smallest guys and merge them together. The fairy godmother is always going to have some tree on the top. And I didn't say this, but here's a fact about binary trees. If you go down to the lowest node, right, find some leaf who's lowest, his sister is at the same height, right? It's also lowest, right? And so those 2 we're going to is what we replaced with those, right? So this was kind of all one case, right? And so the quarter one has the most cases, right? Generally, we don't have that many cases. Yeah. Well, here in this game, I'm also allowing that the algorithm is messed up, right? Maybe the algorithm, right back to our definition of potential value, right? Here, my past could have been really bad. You know, I was in and out of rehab, right? But what's my potential given this, right? It's no longer equals to the optimal, right? Because I've messed up, right? But it's still possible for me to take some step so that my potential doesn't go down even further, right? I mean, if you're going to all join the AA, I would say, you know, you don't cry about the past, right? You say, today, what's my goal today is to do some action that doesn't decrease my potential, right? Right, does that make sense? And so kind of what we're proving here is the algorithm could give me anything here, and it may or may not, it may have crashed and burned. The fairy godmother can give me any ST minus 1. It may or may not be optimal, right? We're not judging these guys, right? And then we're forming, then we have the form ST, right? Yeah.
You can take over the very good this domain work, right?
Yeah. 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 I guess I'm asking, is the current step, right? If I currently decide to do something, well, a greedy algorithm does what feels locally optimal, right? And doesn't look at long-term consequences. And I'm here defining that if you have equality here, then you have what's kind of globally optimal, right? And you want every step to be globally optimal. And if every step is globally optimal, then you get an optimal solution in the end, right? If you tripped and fell a few times, but mostly you were doing okay, then, right?
So let's say we have a problem. We have two medium lines.
Yeah.
We have them they both have the same logic. And so that's the well, like they're both doing their thing. But one of them is more optimal than the other. It's by nature.
No, you're talking about running time in squared, right? Right. All right. So let's separate out what we mean by optimal. We mean by optimal is that it always returns, for every input, it returns a solution which is the best possible solution for that input. We're not saying anything about the running time of the algorithm. All right. So greedy algorithm being optimal means it's returning an optimal solution. Now, it's just so happens I've never seen an n squared greedy algorithm. There might be one out there, but that's just not the issue we're talking about here. Right? They're generally fast. Right? Everybody kind of following this? Should we talk a little bit more about entropy? What we're doing? Does this thing have a clock? No. 50. All right, so entropy, where are we? We're moving along here. All right, so let's go back to we came up with an algorithm that minimizes the number of bits sent, right? So it minimizes this. And so Hoffman codes tell you how to choose all the lengths, right? But I want a nice clean equation, right? If you give me these probabilities, I don't want to have to run the Hoffman algorithm to know what the entropy is, right? So, so here, let me tell you a funny little theorem here. This is just say, if you take any binary tree, and here I'm putting half because it's right. If it's depth 2, then I'm putting a quarter, right? Depth 3, I'm putting an 1/8, right? Depth 4, I'm putting a 16th. And these numbers, what are they going to add up to? They're going to add up to 1, right? You can kind of do some inductive proof to prove that, right? And so, so this is just here. Let's argue that this adds up to 1, right? And 2 to the negative length is this number here, right? Because it's 1, 2, 3, 4, 5. 2 to the negative 5 is 1/32, right? So 2 to the negative length is this number, right? And so if you agree that these numbers add up to 1, you agree that this sum here adds up to 1, right? So that's true for every binary tree, right? But so we could have we could just ask a different question. We can forget about binary trees, right? And we can just ask, can you minimize this number subject to this equation being true, right? And that becomes a calculus problem, right? And I don't think I go into the calculus too much, but one observation is that here we were assuming that each length was an integer, right? And if we relax that condition, right? Now, then there are more ways of choosing your L's, right? Before they had to be L's that meet this condition where they're integers, but now we're relaxing it. So they need to meet this condition, but they don't have to be integers, right? So we're minimizing over a bigger set of things. So our number, is it going to get bigger or smaller? It's going to get smaller, right? Because we're minimizing over a larger set of things. And so the entropy is going to go down a little bit, right? And so if you use calculus, I think you could all do it. It turns out that the LI, the length of the code for a particular object, will be 1 over the log of 1 over pi, right? And here's just a hand wavy argument why that's the case. Suppose all objects had the same value pi, right? Then how many toys would you have? You would have 1 over pi toys, right? And which is 32. And if you had 32 toys, then you take the log of that to tell you how many bits you need to communicate, right? That toy, right? Does that make sense? They were all the same. So this allows us just to narrow in on one object and not worry about any of the other objects. We say, how length of a code should we give this object? And you take the log of 1 over the probability. And that tells you the code length for that one object, right? Does that make sense? And so this then is the definition of entropy. All right. And what is it? It's the sum over all objects of the probability of that object, just like we did before, times how long we should make its code length, right? And we make the code length the log of 1 over pi. All right. So just a couple of years ago, I was on a committee for somebody's master's thesis, and they had this equation on there, and I was like, "Can you tell me anything about this equation?" And they couldn't. And I had this rule that if you put it in your thesis, you should be able to tell me something about it. All right, everybody kind of get this? It's the definition of entropy, and it's useful. All right. Everybody good? So let's just tell you a little bit more about entropy because I think it's cool. Yeah. All right. So so if we really wanted to build a concrete binary tree with just these objects as the leaves, then you're constrained by integers. Yeah. And if you relax that constraint, then it doesn't represent a tree anymore. But you can kind of imagine, suppose I had some object with some really kind of weird probability. And I take 1 over it in the log, and that's not an integer. But it still has some meaning. If I had a bunch of objects and I grouped them together, right? And I sent a message for the group, you can still say that on average, it's going to be right. All right. And another thing to reassure you that it's not so bad, which I didn't say, is that going from the integer version where you actually have a Hoffman code to this Shannon definition where it might not be an integer, it goes down because but it doesn't go down by more than one, right? The total sum, the total entropy is within one, and that's good enough for us, right? And it's a math equation that you can do fun things with. All right. So, right, here's the distribution on the toys, and we can say, what is the entropy of that distribution, right? And it's the expected number of bits you have to tell me for you to tell me an object from that distribution, right? Randomly choose an object from that distribution, tell me which object it is. The entropy is the expected number of bits you have to tell me, right? It's a useful number. And right, so here I just turned it into probabilities, right? It's the same sum overall. All right, so this picture I've drawn so many times in my life because it's the one that both helps with papers and kills them. We can think about this. This isn't a Venn diagram, like this is a set of objects, right? The area of this circle will be the entropy of X, right? We're going to draw a circle whose area is the number of bits I have to tell you something about X, right? So if I'm going to tell you something in X, it costs me the area, right? So so now, what's the entropy of X, Y, right? It's how many bits do I have to send you? I'm going to sample X and Y, right? I'm going to tell you both X and Y, right? And so the area of this, right, is the area that I have to tell you X and Y. And you'll note it's smaller than telling you X and telling you Y, right? Why is that? Why could they be smaller? All right, so it has to do with dependence and independence, right? Suppose X and Y were completely independent facts, right? I tell you something about you and I say no something about you, right? If those were independent, then the number of bits I need to tell you about both of you would be the sum, right? But little in life is independent, right? The fact is you're both taking this course at York, you both chose to sit reasonably in the same place. You're not independent random variables, right? So once I knew something about one of you, it kind of helps me telling you something about the other because they're dependent on each other, right? Conditional probabilities is suppose I told you Y, right? We go into a random universe where we have values of X, Y, and Z, and I told you Y. Now I have to tell you less about X, right? Because this is actually going to be called the mutual information, right? Right? And it's conditional, right? It says condition that I tell you Y, how much more do I have to tell you X, right? The area in here is a funny term. They use I instead of H for entropy. And it's, if I tell you Y, how much does that reveal to you about X, right? Or in fact, here's a funny thing. It's not obvious that this is true, but it is true. If I tell you X, if I tell you Y, what do I learn about X? Is equal to, if I tell you X, what do you learn about Y, right? And if this piece in the middle is empty, right? Then I learn nothing about X from learning Y, and they're independent random variables. Yeah. Yeah, So maybe you are a random person in the world, and he's the person sitting next to you, right? So if I learned that you were in Canada and that you were at York, then I would learn something about him, right? All right, and this, remember when I told you that intuition gets messed up? It's because the area of this piece can be negative. All the other areas have to be positive, but this area can be negative. What does that actually even mean? So here's just a fun example, all right? So X and Y are going to be independent random bits, right? And Z is going to be their parity, i.e. are they, if you have an even number, an odd number of ones, right? So if I tell you, so this area in here, if I tell you X, where did it go? If I tell you X, what do you learn about Y? Well, the sum here is 0, right? Because if I tell you X, you don't learn anything about Y, right? Because they're independent random bits, right? But here's the problem. If I tell you X and Y, right, it completely determines the Z. So this area is 1 because, right? So, and this actually comes up in life, you know, X, Y, and Z are, you know, we know that the total parity is 0. You know something there. Well, if you learn X, what do you learn about Y? Well, you don't learn anything about Y or Z. But if I learn X and Y, suddenly I know Z, right? So it gets, you can see how that makes your life hard in terms of what do I know and what do I not know. All right. Everybody good with entropy? Yeah, well, so you get that Z is the parity of these, right? You know what that means? So if I told you X, do you learn anything about Z? I mean, they're completely, if I know, right? So I mean, here's X, Y, it could be 0, 0, 0, 1, 1, 0, 1, 1, right? We got 0, 1, 1, 0. Right? If I told you that X was 1, right? It doesn't tell me anything about Z. Z could still be equally 1 or 0.
I guess I don't understand negative areas.
I don't either. I don't either. All I know is that here the area of this piece is 0, which is what we want it to be. Right?
So how much if you know X, Y, and Z, then you would know like 2?
If you know X and Y, well, you could know Z, but I'm saying if you know X and Y, then you could determine Z. Right? Z is a function of X and Y. Right? So if you learn X, you learn nothing about Z. If you learn Y, you learn nothing about Z. Right? But if you learn them both, suddenly you know everything about Z. And so that's why these 3 pieces add up to 1. Because if I learn X and I learn Y, then I know everything in here. But what do I learn about Z? I learn about Z this much. And I learn 1 about it. And similarly, if you look at any circle, the area of every circle is 1, right? Because it's 1 bit of information. Right? So out here we got area 0. I don't know. We know 1 about, but 1 is everything. There's only 1. Z is 1 bit, right? If I give you one random bit, what's the entropy of one random bit? It's 1, right? I mean, because I have to tell you 1 bit to tell you it, right? So Z has entropy 1. So that's why the area of this circle is 1, right? And if I told you X and Y, then you learn Z, right? But similarly, if I told you Z and Y, you can solve and find out what X is.
So the numbers don't work with, so do the numbers represent the area? Like -1 is the area of that function?
I don't know what this -1 means. All I know is that if you solve the equations and if you want this area to be 0 and you want this area to be 1, then this is the only way of making that happen. And yes, it's caused me much grief in my life.